everyone, welcome back to Spectrum classes. The sixth video on the topic phase diagram. And in this video, we are going to discuss about the Clapion equation and Clausius-Clapeyron equation in context with the phase diagram. These two equations tells us about the location as well as the slope of the phase boundaries. What is called phase boundaries? Here we are having the phase boundaries. These bold lines shows the phase boundaries. So phase, solid phase and gas phase and their interface is represented by this black line. And here we are having different type of equilibrium conditions of different phases. So here I have drawn one phase diagram, and in this phase diagram first we are going to discuss about the phase transition. What is called phase transition? So phase transition, you are very much familiar with this word. So I am again going to summarize it over here. So here suppose we are having the solid phase. So I have written over here solid. And when this solid is converted to liquid, then this conversion from solid to liquid of a pure substance is called phase transition. And this conversion from solid to liquid is called melting. And the reverse conversion from liquid to solid is known as freezing or condensation, right? So here we are having one equilibrium within these two different phases, solid and liquid phase. Here along this line, this is the boundary between the solid and liquid phase, and these two are in equilibrium along this boundary line. So this equilibrium is called melting from solid to liquid if conversion is there, and if liquid to solid conversion is there, then that is called freezing, right? Now coming to the next equilibrium. So here we are having this bold line, and along this line we are having the equilibrium situation between the liquid and gaseous phase. And when liquid converts to gas, it is called vaporization. And when gas converts to liquid, it is shown by the red arrow, it is called condensation. Similarly, there is another equilibrium between solid and gas phase. When solid converts to gas, then that is termed as sublimation. And when gas converts to solid, it terms as condensation. So these are the basic points about the phase transitions. One more thing which I bring to your notice is that when one phase of pure substance converted to the second phase, that at that moment temperature doesn't raise. So this is important. So if we draw the Tg for this, Tg means thermogram. So temperature versus weight loss. So if we have solid over there, then straight line curve is obtained when the phase transition occurs, right? So at this moment temperature doesn't raise along this phase transition. So this is called phase transition, and during the phase transition no temperature raise occurs. So this is called phase transition. Now two more points are there. This is called triple point, and triple point is defined as the point where three different phases, solid, liquid, gas, meet at one point. Now coming to the critical point. So critical point is what? So first we must understand the critical point. Suppose we are having a sealed vessel, and in this sealed vessel we are having the liquid here, and as the temperature raises, the vapor formation takes. So on increasing the temperature, the density of vapors is increasing and density of liquid decreases. At one point of temperature where the no more liquid is there, only vapor phase is there. So this point of temperature is known as critical temperature. And this type of vapors or fluid is known as superfluid. So beyond this critical point or critical temperature, no more liquid is there. So we cannot extend this curve beyond this critical point. And at this critical temperature, the pressure of this system is known as critical pressure, which is represented by PC. So this is the basic terminology which we are going to use here. Now coming to the Clapion equation in reference to the phase diagram, because this Clapion equation gives us the slope of this curve at different points for different kind of equilibrium, right? So first we will solve the Clapion equation, and then we will going to apply this for different kind of phase transition, right? So phase transitions and phase boundaries. So suppose first we are going to consider that there is an equilibrium between the liquid and as well as gas phase. Now we are considering two different points along this line at which the pressure is P1 and P2, and their difference is taken as delta P. And similarly for the temperature corresponding to these pressure lines, we are having T2 and T1 temperature, and their difference is considered as delta T. Now coming to the Clapion equation. At particular pressure and temperature, the two phases are in equilibrium. So along this equilibrium, the thermodynamic condition for the equilibrium is that the chemical potential of the substance in the gas phase is equal to the chemical potential of the substance in the liquid phase. So these two are equal. And since we know for one component system, chemical potential is equal to the molar Gibbs energy. What is called molar Gibbs energy? Gibbs energy per mole of the substance. So this is called chemical potential. I will make a separate video on this chemical. As we all know that Gibbs energy is in relation to the change in pressure and temperature can be written like this. So dG, change in Gibbs energy, is equal to V dP, change in pressure, minus S is the entropy, dt, change in temperature, and here V is the volume. If we write this equation in terms of molar values, then it can be written as dgm Vm dP minus Sm dt. So m stands for molar quantity, and dgm, since gm is equal to mu, so I have replaced this d mu. Right, so this is our equation number 4, and the change in chemical potential for alpha phase is exactly equal to the change in potential for beta phase. So here what we have done, this is our equation number 4, and these values for alpha phase and beta phase we are putting in the equation number 1, right? So I have written over here this Vm alpha dP minus Sm alpha dt is equal to Vm beta dP minus Sm beta dt. I'm just writing this is mu alpha and this is mu beta. So in this manner you can equate these two equations. Now we are collecting the values for volume and pressure on one side of the equation and entropy and temperature on one side of the equation. Right, so Sm, this is negative here, this will come if this side, then Sm beta minus Sm alpha dt, dt is taken common, is equal to Vm beta minus Vm alpha dP. So here in this manner you can write down this equation. So this is our equation number 5, right? Now if we further solve this, so change in entropy from beta to alpha phase. So here if we are moving from liquid to gaseous state or gaseous state to liquid state, then this is called transition. So we can write down delta S transition into dt, delta V transition and dP, right? So this can be written like this. Now here I am having dP, so dt will be in the denominator, so dP upon dt here in this side, and delta S transition upon delta V transition we are having here, right? So in this manner we are going to equate this equation, and this equation is known as Clapion equation, right? So this is in terms of phase transition. Now if we are moving further, then this delta ms or delta MV, M stands for molar again. Now this delta S, that is entropy of the entropy of transition, is equal to enthalpy of transition upon T, or sometimes you may know dq upon T, right? So this is entropy value, and if we put this value in this equation, then what we will get? We will get dp upon dt into, instead of this delta S transition, we are just putting the value of delta H transition upon T here. So in this manner, you can understand. Now, this is again known as the Clapion equation. So in either manner, you can identify this Clapion equation. Either dp upon dt is equal to delta transition M S upon delta transition V, or delta H transition upon T delta V transition, right? So in either terms, you can determine this. Now, the Clapion equation is an exact expression. So it is important. It is an exact expression for the slope of the tangent. If we draw a tangent over there, then on here we are having at this point, it is a tangent. So to the phase boundary at any point and applies to any phase equilibrium of any pure substance. So this is how this Clapion equation is important. Now, if we revert this equation in terms of dt upon dp is equal to delta Vm upon delta S, right? So this equation suggests us the change in boiling point and freezing point with the application of pressure. So change in temperature of boiling point or freezing point with the application of change in pressure. This equation will give us this information also about the phase transition. Now coming to the application of this Clapion equation to the different phase transition, right? So here suppose we are having an equilibrium. Here we are having melting and here we are having freezing as we discussed earlier. So suppose melting temperature is T star and melting pressure is at P star, represented by P star. Then we can put here dp upon dt. This is known as fusion, right? So transition, rather writing transition, which is a common term, and since we are applying this to solid and liquid phase, so we can use over here as a fusion word. So delta H fusion upon T delta V fusion. So this is the Clapion equation, and if we integrate this in terms of change in temperature and pressure, so P star to P dp is equal to delta H of fusion upon delta V of fusion dt upon d T star to T. This I can write for the biology students too. So what I have done here is I am just writing it over here. So dp is equal to delta fusion H upon delta fusion V into 1 upon T dt, right? So if we are applying the integrals, then it will be like this if these two values are constant. And to apply the limits, so P star is the melting. For fusion, we are moving further. So P star to P and T star to T for dt, right? So this is what I have done over here. Now on solving this integral, what we will get for dp, we are having, again I am just writing for dp, we are having P star to P is equal to delta H of fusion upon delta V of fusion, and 1 upon T is equal to ln T, and on applying the powers T star to T. So on putting these values, what I will get? P minus P star upper limit minus upper limit is equal to delta H of fusion on delta V of fusion ln T minus ln T star. Okay, so ln T minus T star, when we are having natural logarithm T minus T star, then it can be written as T upon T star. Okay, so this is what I have done over here. So this minus P I have put on the right hand side, and therefore I will get P is equal to P star plus delta H of fusion upon delta V of fusion ln T upon T star. So I hope you understand what I have done over here. Now coming to the formula. So if we are having this ln T upon T star, then we can also write it in the form of ln 1 plus x. So if we are having 1 plus T upon T star minus T star upon T star, I have written. So T star will be cancelled out. We are having 1. 1 upon T star minus 1. Minus 1 to minus 1 will be cancelled out. So we get T upon T star from where we have started. So T upon T star can be written in terms of 1 plus x in this manner, right? So what we are going to move further. So here we are having P is equal to P star plus delta H fusion. What we have written over here, this whole thing we are writing here as such. And instead of this ln T upon T plus, we are simply write ln 1 plus x can be written as x plus 1 by 2 x square. But we discard the further terms. So we simply write down only x. So what is x? This is our x. What I will write, T minus T star upon T star. So that T star which I should write over here, that is here only, T star. So in either manner you can write down, right? So this is how the Clapion equation can be solved for the solid and liquid phase. Here the transition is termed as fusion. Okay, so we will get the value for the pressure on changing the temperature, right? So now coming to the next equilibria. So next equilibria is in the liquid and gas phase. So here we are having the equilibrium between the liquid and gas phase. So this is called vaporization, or gas to liquid is condensation. And therefore what we will write over here, instead of transition, vaporization. That is familiar to us. So dP upon dt is equal to delta V vaporization, H upon T delta V vaporization. Now, since for volume of gas is very much higher than the volume of liquid, we all are aware about this fact. And since we are talking in terms of change in volume, so change in volume when vaporization takes place, that is, we are just assuming that it is equal to volume of gas or vapor. So on determining the change in volume, V2 minus V1 means V gas minus V liquid, and V gas minus V liquid, since V gas is very much higher than the volume of liquid, then therefore we are writing as V gas. Okay, and we are considering here that this V gas or vapors are behaving as ideal gas, therefore PV is equal to RT for ideal gas. Or we can say PV is equal to nRT, or P upon V upon N is known as PVM equal to RT. So this is our ideal gas equation in terms of molar. If number of moles are more than 1, and if number of moles are 1, PV is equal to RT, right? So here delta V vaporization is equal to V gas is equal to, if it behaves like an ideal gas, then it will be equal to RT upon P. And on substituting all these values in this equation, what we will get, instead of delta V vaporization, I have put RT upon P, and this P will go to here. Okay, and how we are going to write this, dP upon dt is equal to delta H vaporization upon T square, T into T square, RT square, and this P will go to here into P. If I rearrange this, then dP upon P is equal to delta H vaporization upon r dt upon t square, right? And this dp upon p is written as d ln p, as we did in my previous slide for d ln t, right? So this can be written like this. So I have write all such things over here, that here dp upon p is equal to d ln p, and d ln p upon dt is equal to delta h vaporization r t square, and this equation is known as Clausius-Clapeyron equation, and this is the approximate value, since we have made two approximate, and this equation is applicable for this vaporization and condensation equilibrium, right? Now on solving this, d ln p is equal to delta h vaporization r t upon t star dt upon t square. So on solving this, what we will get? We will get ln p upon p star is equal to delta h vaporization upon r, and for this type of integration we are having 1 upon t minus 1 upon t. So we are getting this value for this Clausius-Clapeyron equation on further solving about the information regarding this liquid to gas equilibrium, right? And here what I have discussed earlier, here we are having the critical point, and beyond this critical point we cannot extend this curve or this line, because no fluid, no liquid is there anymore after this critical, only vapors are there, right? Now coming to the next equilibria, that is between the solid and gas. So this solid and gas, we are having the sublimation and condensation. So rather writing this transition, we are writing sublimation. So here I have written this delta sublimation H upon T delta sublimation of V. Right? So here, as we all know, this delta H sublimation is equal to delta H fusion. Fusion means first solid to liquid, though it is not there, and then vaporization. Therefore, if we evaluate this equation, then we get more steeper curve than this liquid gas equilibrium. So this is what we have done here. We understand the application of Clausius-Clapeyron equation for different type of equilibriums existing for pure phase compound. How this Clapion equation gives information regarding the exact slope value for the phase boundaries, right? So I hope guys you understand the concept which we have discussed here, and if you like this video, please give me a thumbs up, share this video with your friends, and subscribe my channel. Thank you all. Thanks for watching.